Hi, I'm DJ Ware. On this episode of the Cyber Gizmo, I'm going to be covering what happened at the RISC-V Summit for 2022 right after this. So the first place to start out is with the keynote, and this was given by Callista Redmond, who is the CEO of RISC-V International.
For those of you joining in person and for those of you joining online around the world, thank you for showing up all year long, and especially as we cap off the year, celebrate what we've done in 2022, and look forward to an incredibly bright future. There are three things that I want you to come away with. Number one, RISC-V is inevitable. It's here already. It is going across all domains in computing. It is inevitable. There's no turning back. Second, RISC-V enables the best processors. Now, you can define best in many different ways. Is it the lowest power? Is it the highest performance? Does it fit into the constraints and meet the challenges that your design is seeking to overcome? And number three, RISC-V is rapidly building the strongest ecosystem. And that ecosystem is profound. And it makes business sense. It makes business sense to diversify your business interests, to run on multiple architectures. As we continue to build on the RISC-V ecosystem, by the way, this is just a sample of where we are today, I expect that we will meet or exceed more than 90% of the key pieces of software needed in modern-day architectures within the next single-digit years, 2 to 3 years. This is not a project that's going to take us decades because we have done this before. There is not just one architecture choice out there. In fact, there are many. And it is in software best interest to run on multiple architectures. Let's talk about that investment. Tens of billions of dollars have been invested in RISC-V. We see this inside of companies. We see companies like Intel planting $1 billion flag on RISC-V. We see companies like Sci-Fi, MIPS, Alibaba, Andes committing entire roadmaps to RISC-V. This is a strategic, long-term, durable choice. This is not a choice to meet your quarterly metrics. This is a choice for the future of computing, for the future of those companies. Billions of investment have also been coming in from governments around the world. We earlier this year saw India commit to RISC-V. The European Union, many different calls for tender. I think one just came out last week. We're continuing to grow pretty quick, about 26% in the last year. Today, we have more than 3,180 RISC-V members, and I signed 2 more this morning.
There have been a number of vertical markets that have opened up this year that were not normally there for them. So the first one is in the vertical markets. I call them verticals because they have to do with specific lines of business. So the first one is automotive. The RISC-V people are expecting about a 10% market share by 2025.
In automotive, Mobileye has been committed to RISC-V and continues their investment. In Paris, working together with NSI Texi. I was in Tokyo recently, and automotive is absolutely igniting on RISC-V. Imagination coming out with their automotive solutions along with MIPS this quarter. Sci-Fi has been deeply engaged in RISC-V around automotive as well as many other parts of the portfolio.
A new one has entered since last year, and I didn't think anybody would think this was possible this soon, but there is a data center offering now, and that's expecting a 14% market share by 2025 as well. Overall, chip market growth will be over 115% year over year.
What about data center? We hear about data center a lot because that signals scale, volume, right? Esperanto with their very high performance core designed for AI. Alibaba also using RISC-V in their data centers. Their one-chip processors have both open as well as Alibaba-specific opportunities. Ventana, a newer company for the world, is bringing out all kinds of great progress. In fact, we heard a little bit about that yesterday in their high-performance processors.
Telecom and communications, one of their partners is Qualcomm, and Qualcomm is using the RISC-V in a support chip role for their Snapdragon processors. There are others. Google's Pixel is based on RISC-V, or has a RISC-V chip in it, I should say. So all the SoC RISC-Vs will grow by 21%, and that was between 2019 and 2027.
Telecom and communications, Google with their Pixel 6 Titan RISC-V processor, Espressive, bringing dual-band Wi-Fi and BLE to a RISC-V chip. Alibaba, instrumental in bringing Android to RISC-V. And then Cypiad with their chip running Android 10. There's a lot of progress going on here, especially around 5G as we look to Andes and their leadership.
Consumer IoT devices has the largest market share of 28% by 2025.
Consumer and IoT devices. Android open source project on RISC-V now accepting numerous patches. Our next step is getting Android certified on RISC-V, and we are well on that path together. But these many examples have shown us not just the potential, but the reality of RISC-V. This is not an experiment. This is today. This is your day job.
AI and machine learning expect RISC-V to grow by 73% in 2027. I don't know what the market share will be. There are some really big players in that space.
AI and ML, as I mentioned, Alibaba has been using RISC-V for AI processing specifically. Andes has leveraged the vector capabilities of RISC-V, something that allows for profound differentiation. And Fraunhofer coming out with their edge AI devices as well. In fact, AI, acceleration, these are the kinds of capabilities that we see and hear from multinationals and hyperscalers as adding on to their existing capabilities.
Another new market is high-performance computing. Now, I know the Barcelona Supercomputing Center has been looking into using RISC-V. It's one of the things they promoted a few years ago, that they were interested in using RISC-V as their processor. But there have been a number of other supercomputer centers around the world that are interested in RISC-V as well. In fact, there's a lot of research going on right now to see how RISC-V can be placed into the server space to be able to do complex math. And they're experimenting with vector and a number of other things. But right now, I would say that is in the research phase and in the investigation phase. Christie, one of the founders of the RISC-V International and also is a founding member of Sci-5, talked about RISC-V ISA profiles.
And talk about one of the more important things we've been doing on the technical side of RISC-V, which is defining these profiles. So I'll talk about profiles in the profile roadmap. So we all know RISC-V is a modular, extensible ISA. There's a base ISA, there's standard ISA extensions that add new features. You can have custom ISA extensions. So this is great, and nobody wants to get rid of this flexibility because a lot of products, this is exactly what people want. So why are we developing these standard ISA profiles? If you have a large software ecosystem, like distributions for a rich operating system, you really need uniformity across RISC-V systems. It's not practical to recompile QA tens of thousands of packages for different platforms. So everybody's going to benefit from having this uniform profile of RISC-V ISA features. But I want to emphasize, RISC-V world does not now become only profiles. RISC-V world is much bigger than profiles. Profiles are only for this small part of the world, which is application processors. Right? There are many, 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 many other kinds of processor in the world that will all be RISC-V. They don't need profiles or don't seem to need them. Right? This talk is really about profiles for application processors. Now, those are often the stars of a chip. You view these as the big high-end cores. And they're important because they have so much software running there, and that software is what really needs these profiles. But we're not getting rid of all the other uses of RISC-V, right? So the talk is mainly about profiles, primarily for application processors, or only for application processors, but the rest of RISC-V world is still there, not going away. So what's the goal of the profiles? The two main goals are reduce optionality and also the granularity of the optionality. So there'll be a few pretty coarse-grained options, and subset of those options are not an option. You either do the whole option or none of it, right? So reducing the optionality and the granularity of the options. We're also raising RISC-V capability over time. Now, combination of points 1 and 2 means there's going to be an increasing amount of mandatory stuff you have to put in a RISC-V application processor to be compatible with the profiles. So we have names, so we have a naming scheme. So profile name strings begin with RV for RISC-V. There's actually two kinds of profiles. I lied a little when I said we're only doing application processors. For the purposes of branding, we defined RVI to be generic unprivileged ISA, and this is really so people can say they have something that is RISC-V, right? So RVI is generic unprivileged instructions. RVA are the profiles for application processors, and I'll focus mostly on those. So another component in the string, so you'll have RVA, and then a number string, which is a number of years after the year 2000. So 20, 22, 23, 1047, you know, long distance future, will be RVA back then, right? The most privileged mode in the profile. So when we define, I'll talk about this a little bit more, supervisor mode profile isn't only for supervisor mode, it's for user mode and supervisor mode working together. So when you define a profile, you define the outermost privilege mode in that profile. And so there are different profiles for just user mode versus supervisor mode. And then the X-line of the base ISA, 32, 64 for now. So some examples, RVI 20, U32. This is unprivileged generic instructions for a 32-bit RISC-V core. That's that profile. RVA 20, S64, on the other hand, is application processor profile of supervisor and user mode. Just to go over the specific ones we're developing, so RVA 20 is basically what we did is encode the Unix standard for RISC-V that's been around since 2016. So at a workshop at MIT in 2016, we kind of sat around and said, what should be the standard thing that distros compile for, talking to the folks at Red Hat. And we said, okay, it's RV64GC, right? Plus what happened to be in the systems around at the time in the privilege level. So basically went back and more formally encoded what was the de facto standard back then, and we call that RVA 20 because most of the specs were ratified finally in 2019. So that's why we're going to call that RVA 20. And so that is the de facto standard that most distros are using right now, is that RVA 20 standard. And we're just formalizing its name. So just to go over, people talk about RISC-V and fragmentation, hundreds of options. You actually go look at Linux land, what is there? So in RVA 20 U64, user land ISA, most things are mandatory. The only option you have is where the performance counters are visible or not. That's actually the only option. How are we going to manage evolution going forward? So the plan is to keep an annual cadence of new profiles, at least for now, so one a year. But that's hard for the whole ecosystem to keep up with. It's important, though, to have that progression for all the vendors and everybody else producing stuff. But what the idea is we're going to designate certain versions as major releases every few years. And the idea, those are ones that ecosystems can sort of anchor on and assume this is a good point to build on and maybe stay stable for a while on those major releases.
The third thing to talk about is Ventana. Ventana is a new company. They're both very experienced. They have over 30 years of experience in developing chips and bringing them to market.
I'm Balaji Bhakta, founder and CEO of Ventana Micro. It's a momentous day today for the entire RISC-V community. When I say that, I'm not saying it lightly. It's a hugely important day for the RISC-V community as well as for Ventana Micro. Today, Ventana brings RISC-V architecture to high-performance data center and other applications using RISC-V architecture for the first time in the world. So it's a great time to be part of the RISC-V community, and the opportunity for us to have RISC-V play at the same leagues as any other ISA, going after every application possible and available to CPUs, right from low end all the way to the data center class, is made possible thanks to Ventana's product that we're going to talk about today. World's first RISC-V-based data center class, high performance, highly efficient processor in the world. Veyron V1. And to talk about the underpinnings of this particular solution, I'm going to ask Greg to join with me and walk us through some technical aspects of what Veyron V1 is all about. Greg.
What makes up a data center class CPU? It starts with a high single-thread performance. And to get that, what we've developed is a wide, aggressive, out-of-order CPU core. A sophisticated front end, decoupled predict fetch, large B2B branch predictors, then feeding a wide decode pipe, feeding a wide execution back end. The second important thing is scaling efficiency. As you scale up to high core counts to have a high scaling efficiency to the performance that you're still getting out of those cores. What enables that is a couple of things. One, a very substantial cache hierarchy. Even just within our compute cluster, as we call it, within a chiplet, is a 3-level cache hierarchy. As you can see, each core has its own private 1 megabyte of L2 caches. And then there's a further 48 megabytes within the cluster level L3 cache, so 64 megabytes in aggregate. Now, going up to the package level, where you have a multi-chiplet-based system, we efficiently support a hub-and-spoke type of architecture, where there's a hub with a lot of die-to-die links to connect a variety of different chiplets to that hub. It can be one to many Ventana chiplets, depending on the kind of core count you want to scale up to. Typical standards you have within SoCs, both CHI and AXI. It also then can go on top of, today, on top of the BOW, a bunch of wires, ODSA standard. And tomorrow, it'll be on top of UCIe as well. And the key thing with that data solution that we've architected is foremost very low latency, along with low power and high bandwidth. But that's a key thing to support this idea of disaggregating the chiplets while trying to minimize the impact of those die-to-die crossings, so that you really have the appearances from a performance perspective, from a NUMA perspective, as if it was a monolithic die.
And those are expected to have a board for that chip sometime, I believe he said mid-summer of 2023. And after their testing, they believe they will be bringing it to market sometime in 2024. Canonical was there, and they were talking about their efforts to bring Ubuntu onto the platform. Now, currently, there's a number of Linux distros that are there. Ubuntu is running on RISC-V today. So in addition to Ubuntu, you have Debian, Fedora, SUSE, Gentoo, and Yocto.
In the afternoon session, it's really great to have been working 1 year, or the last year, seeing all this progress that we have made together as a community, and it's really startling to be here. My name is Heinrich Schuchert. I'm working for Canonical as RISC-V lead engineer. 5 is a first-class Ubuntu architecture. We really want to give you all the same tools that you see for the other architectures. And to do this, of course, means, first of all, spinning out images for the hardware that has come available. So it really started in the last year when we supported the first boards that were on the market, the Unmatched, the Unleashed board, where we could run Linux on. But now we have released images for the next boards, for the Vision 5 board, for the All-Winner D1, for the IP Lishi-RV. Now we have the next boards that we are going to bring up in February. We want to bring out support for the microchip PolarFi Icicle kit, and we have started to work on the Star 5 Vision 5. But there are also some pain points with the hardware that we currently can get. The biggest pain point from it that we see when we try to build packages is that we are missing the hypervisor extension. So we cannot run a VM on RISC-V with good speed. And that means we are currently using x86 servers to build all the packages. And that, of course, limits capacity. We also have seen that many of the products are really short-lived. I mean, the images that we brought out for Unmatched and Unleashed, how far are they still relevant if you cannot buy the boards anymore? And if you look into performance, what we have reached now is the level of a Raspberry Pi 3. There's nothing really server-grade around. Let's look into the software side of it. I just counted how many binary packages exist for different architectures, and if you put x86 at 100%, you see 93% of the packages are available on RISC-V, and ARM is somewhere in between the two. And so you can do a lot of things already in this ecosystem. If it comes to development, you have Python available, OpenJDK, Node.js, Go, C, C++. There's one that is .NET, which currently is being available only on ARM and on x86. If you look into virtualization and containerization, we are spinning images for QEMU, for Docker, and for LXD, so that you can easily run your containers in RISC-V. You can, of course, have the emulation also inside RISC-V. When it comes to desktops, I've been running a desktop GNOME, I've been running KDE, I've been running XFCE, so all these desktops environments are also available for the ecosystem, and we are currently spinning server images. You have to load those packages on extra. Maybe at some time we will start spinning desktop images, but currently there is no system out there that's really that performant that you say it's your daily working instance of the operating system.
He talked about testing GNOME and KDE, XFCE. He said they can run on RISC-V, but again, because of the performance on the hardware that they have currently, the performance is nothing to write home about, probably not something you would want to use either at this stage. Now there are new SoCs coming, and there are new development platforms that are coming to address this. What about development boards? What's happening there? Obviously, we need something. We've needed something for some time. Well, Sci-Fi has teamed up with Intel and their foundry, the Intel foundry, and Intel is working. They actually delivered the I think it was a real board, not a prototype, a real board at the conference this week to show off what they were doing. This is a micro ATX form factor that is based on the Sci-Fi P550 chip.
Well, thank you all for coming and joining us today. My name's Sam Grove, and I'm joined by Nikhil from Intel, and we are going to talk to you about the highest performance RISC-V development board. So the next board that's coming is the Hi5 Pro P550, and this is going to be the highest performance RISC-V development board on the most advanced process. So today we'll give you a bit of an introduction to the development board and the features, as well as the capabilities and what's inside the SoC, the soul of the machine. So if we start and look at the CPU, we have the Sci-Fi Performance P500 series quad-core CPU. And this is a RV64 GBC ISA with Sci-Fi Insights Debug and Trace, and private L2 cache and a shared L3 with a streaming prefetcher. So we're expecting to see this thing come back over 2 gigahertz, which is going to push RISC-V software development to much new levels, new heights. Additionally, when we talk about the use cases that we're targeting here, I mean, this is really for people building software, packaging software, and distributing software to the rest of the ecosystem. So if we go a step further and kind of look at a high-level block diagram of the architecture of the board, we're looking to fit this into a micro ATX form factor. And again, at the heart of it is the Intel Horse Creek SoC. And then we fit that out with 16 gigabytes of DDR5 memory and a PCIe switch for expansion. And that expansion is really important because we give more connectability for more cards that you're interested in enabling drivers for. The M.2 key slots are important for Wi-Fi networking or NVMe-based storage. And then, of course, USB 3, for more expansion and onboard graphics and networking. Let's talk a little bit now about the SoC.
So we put together a PCIe Gen 5. It is an Intel 4 process Gen 5 PHY, and a DDR5, which is also an Intel inbuilt hard IP. We put this together with a Synopsys PCIe controller as a root hub, and we also put a DDR5 controller from Cadence. And we also added a 2 megabyte of scratchpad memory that you could use in your development. Now let's look at what features does PCIe enable. It's a Gen 5 root complex. It can go up to 32 GTS. We support up to 8 lanes. Of course, at Gen 5, we probably will be supporting about 4 lanes or 2 lanes, but at Gen 3, we're able to do 8 lanes. On the DDR5, it is the latest generation technology that you see. In fact, to be honest, it's very hard to even find DRAM modules, but we already have it enabled on silicon here. We can go up to 5600 MTS. Just like the PCIe, it has its own embedded microcontroller to manage the training sequence. Apart from that, we have 2 quad SPIs, 1 octal SPI, 2 I3Cs, a UART for debug, which we actively use in the OpenOCD. And we have PWMs, we have GPIOs with slew rate control, and the peripheral transfers between the different peripherals using peripheral DMA. This takes the workload off the main CPU.
What will you enable?
We'll see how that plays out as we get closer. That is expected to be released in the midsummer of 2023, so next year. NASA is also involved with RISC-V. They have a project called the High Performance Space Computer, or HPSC. That is a joint project between NASA, NASA JPL, and leading technology partners in order to bring the next generation computing platform.
So I'm Pete Fiacco, and I'm part of the leadership team at NASA and JPL. And I'm going to talk today about something called HPSC. I hate to start like Star Trek or whatever, but you've heard the Prime Directive, right? Well, we have these guiding principles for what we did with HPSC, and you'll see the kind of little colored box here: radiation hardness, extensibility, high performance per watt, power efficiency is really, really important, industry standards, standards interface, fault tolerant, safe design. So what did we come up with? So HPSC, it's a multi-core RISC-V SoC. But it's really more than that. We're not only delivering the SoC, we're delivering boards, software systems, and a complete ecosystem. We'll talk about this in a little more detail, but protos are available in calendar 24 and fully space qualified stuff in 25. So it's happening pretty quick, especially in a space NASA government mode. I know you guys in commercial side turn things around really, really fast. The government, maybe not so much. But HPSC is making big changes in that space. This is really a significant public-private partnership. That's kind of the way I want to see it. I want you to see it and understand. And we'll talk about some of the major contributors. Yesterday, I think, Microchip had a couple of presentations and talked about their product roadmap, specifically FPGAs with embedded processors. They also talked about HPSC. The reason for that is, obviously, Microchip is our lead partner on this. There's some really significant contributions coming from other people in the RISC-V community. Sci-Fi is contributing the X280, which is the application core. We have 2 clusters, 4 processors each, so 8 processors and application core. Those are X280s. We love the X280 because of the vector capability. Again, I'm going back to the actual HPSC. Here's something about it in terms of, high level. I talked about the RISC-V X280 cores from Sci-Fi. There's a security subsystem in here. There's a kind of like a fundamental a root processor that boots the whole thing. It's the kinds of things you guys all deal with all the time. The HPSC ecosystem. I mentioned we're not just delivering a chip, we're delivering an entire system that NASA's seeding this initial thing, and then industry is going to take it from here. So there's already plans for derivative works. We're going to be building the software ecosystem, board systems, And we're going to be driving interoperability from day one. So there's going to be a whole portfolio of products from Microchip and others that will be completely interoperable.
The estimated prototype should arrive sometime in 2024 for the HPSC based on RISC-V, and they expect a fully space qualified SoC sometime in 2025. And this, as I said, will be the standard processor for NASA's use in all aspects of a NASA-sponsored mission. So you have everything from wearables to cell phones to IoT devices, edge, cloud, and data center, also automotive. And then you also have high-performance computing, and then finally into space itself. So RISC is really coming along. It's come a long way in a year. If you go back and look at the video I did a year ago, you probably think, wow, this is bleak. They're doing stuff, but it looks like we're spinning our wheels and we're not developing anything we can use. One other board I wanted to mention is there is a SoC that was announced at the conference that I didn't cover here. It's called the Star 5 Vision 5 Release 2. And that board is now available. So I think you can buy it for pre-order now. It'll start shipping sometime in January. The specs on the board should be on the Star 5 website, so you should be able to find out about that. I think it's a 4-core with 8 gig of memory, 1 gig networking, and it has a GPIO. Also, it has a number of other, like a camera and all that kind of stuff, the pins for that as well. Raspberry Pi type form factor. But that's all I had today. If you liked the video, please like and subscribe. Hope to see you all again soon. Bye for now.